So for those who are still eager for more statistics, an optional discussion, but of a very important practical issue. How do we deal with missing data? Very often when we have some data matrix, we see that it's not complete. So how can we actually, what do we do with missing data? Some people say, I will just put a mean score instead of missing data. But as we will see very shortly, this is a very bad idea. And we'll discuss the good and the not so good strategies of treating missing data. So first of all, to discuss this issue, we need to make a very important theoretical distinction between three types of missingness, which was proposed at some point by Rubin, I think, and colleagues. There are different mechanisms or different reasons why data in your matrix can be missing. One situation is called missing completely at random, when the missing data are missing just by chance. So imagine that you have a nice table of responses to your questionnaire, and you use a random number generator to exclude some data values from this matrix and leave just empty cells. That would be missing completely at random. Or another situation when the data are missing completely at random are so-called planned missing designs, when your questionnaire is extremely long and you know that participants are not going to be able to complete it fully. So then you randomly mix the sequence of questionnaires in your test battery. And as a result, when people drop out, they complete some questionnaires but not others, but this will also be completely random, which questionnaires they complete and which they don't. So this is called a planned missing design. Or when a person is randomly administered one questionnaire out of 3 different options, then also these missing data are completely at random. However, there are situations when the reason why the data are missing is not completely random. The second situation is quite misleadingly called MAR, missing at random, kind of missing at random, but not completely. And it's a situation when your missingness systematically depends on some other measured variables. So you can predict why you can predict the fact that this answer will be present or not present if you know some other characteristics of that person. So for example, some people did not complete some tests at the end of your questionnaire because they had very low motivation to complete your tests. But if you have measured this motivation, you can predict this missingness. And this is called missing at random. And the most difficult situation is called missing not at random, when your missingness depends on some unmeasured variables that you don't know about, or, which is even the worse, it depends on the value of the missing data itself. For example, your missing scores on an IQ test because people did not understand the instructions. They had very low IQ, and as a result, you have missing data, but which depends on the value of the measured data itself. So here is an illustration of it's an artificial data, just an example I found online. So you have people working in a company, they have IQ, they are ranked here by IQ, and you have job performance ratings given by supervisors. So this here is complete data, and here is the situation of missing completely at random, when the data are missing just by chance. The second situation, missing at random, it's a situation when people with low IQ do not have any data on job performance, but you have IQ, so you can predict this missingness. And the third situation is the worst, when the data are missing not at random, there is some other reason why people with certain adjacent IQ scores their data are missing. Maybe they work in the same division where maybe their boss is awful and they didn't want to give them performance evaluations and so on. So there is some systematic reason, but you don't know it. And this is missing not at random. Another funny illustration that I found online is by this guy, Richard McElrath, who defines missing data types as reasons why a dog might eat your homework. So here A is some attribute of student who completes homework and reasons why homework can be better or worse. And there is a missingness mechanism, which is a dog, which results in the homework results with missing parts or with missing homeworks. So if a dog eats just any homework by chance, this dog is completely independent of the attributes of the student, and it's missing completely at random. The second situation, missing at random, when this missingness mechanism systematically depends on some measured properties that of the person who completes this homework. So you can predict, if you know who the student is, you can predict that the dog might eat their homework because maybe they leave this homework somewhere and where the dog can eat it. But the worst situation is missing not at random, when the reason why the dog eats homework is predicted by the homework itself. For example, when the homework is bad, the dog eats it. And research-wise, missing completely at random is the best situation because it's the easiest to deal with. Missing at random is slightly harder. It's slightly harder because you need to use more robust approaches to model your missing data. And missing not at random is the worst situation because there is often no way to obtain unbiased estimates of the statistical effects that you are looking for. So your missingness is going to affect the results of your analysis in some kind of unpredictable ways. So that's why when you conduct your missing data analysis, you typically start by figuring out what type of missingness you have. And in order to answer this question, you can either think of the reasons why some answers are missing in your questionnaire. And if you expect that probably these answers are missing completely at random, you can test this statistically. There is a special statistical test which is called Little's test of missing completely at random by a guy whose name was Little. In SPSS, there is a module called Missing Value Analysis in Analyze, and there you can tick EM checkbox. And if you do it, you select the variables for which you want to investigate missing data, and as a result, you'll get Little's missing completely at random test. So if this test is not significant, just like Kolmogorov-Smirnov, if this test is not significant, it means that probably your data are missing completely at random. But if this test is significant, probably your data are not completely randomly missing. There is some kind of systematic pattern in the distribution of missing cells in your matrix, and probably you need to apply some more robust approach to deal with missing data. With missing at random, the good news is that it's not possible to distinguish empirically between the bad situation and the extremely bad situation. Missing not at random, you can only theoretically hypothesize, but you cannot distinguish between missing at random and missing not at random. For missing at random, you can try to predict this missingness. You can create variables that code missingness, In SPSS, you can do it with the function compute. New variable equals missing of old variable, and then this new variable will contain zeros for values of old variables that are not missing, and ones for variables of old variables that are missing. And then you can calculate some kind of correlation coefficient to just see if this missingness is systematically related to some other measured variables. However, it is kind of optional, because anyway it's impossible to distinguish missing at random and missing not at random. So if your missing is not completely random, you just try to use a more robust approach, but you don't know whether it will be completely efficient. So what are the approaches that we can use to deal with missing data? There are some procedures that are really bad. And the bad news is that in SPSS, they are often available by default. SPSS proposes to us a choice between listwise deletion and pairwise deletion. Listwise deletion, imagine that in your questionnaire you have 500 questions, and if a person has not answered one question, their answers will be completely excluded from your analysis. So if at least one data point is missing for an observation, this observation is excluded from your analysis. Now, of course, if you only have a couple of people with responses missing, this is not a problem. It won't make much of a difference. But if half of your respondents have missed one question in some place or other, because your questionnaire is very long, by using listwise deletion, you will lose a lot of information. And also, if there is a systematic reason why the data are missing, if you exclude people who have some missing data, you will restrict your sample only to people whose data are not missing. As a result, your estimates will be biased because your correlations will be calculated, for example, on the group of more motivated individuals, and you will not know what these correlations are supposed to be if you included people who are not so motivated and who did not complete all of your questions, or who are not so attentive, for example. So there will be some confound variable that will interfere with your estimates, the cause of missingness. Another approach, which SPSS proposes to us by default, is pairwise deletion. When we calculate pairwise associations between variables, for example, we calculate a correlation matrix, and for each pair of variables, we use the individuals who have scores on both variables. So if a person has skipped an answer, they will not participate in calculation of this particular correlation where this particular answer is needed. But for all other correlations, they will be used. This is kind of more efficient because you try to use most information in your data. And if your data are missing completely at random, it's no big deal. The estimates are still unbiased. However, if your data are missing at random but not completely, you might have a problem. Imagine that half of your respondents did not complete a certain questionnaire because they were not motivated, for example, or because they did not understand instructions. As a result, some part of your correlations will be based on full sample, and another part of your correlation matrix will be only based on those people who completed this questionnaire. So if in SPSS you will see the number of individuals based on which every correlation was correlated, and if you see that these numbers are very different, you have a big problem. You have a problem substantially because these correlations are based on incomparable samples, even though they are in the same matrix. And also you might have a problem if you try to apply more complex statistical approaches like factor analysis to this correlation matrix. There might be all kinds of warnings that it's ill-conditioned and it's not invertible, so it will be a pain to deal with. So we want to get rid of empty cells if we have missing at random. How do we do it? There are two fairly primitive ways of doing it. One very primitive way is called mean substitution. Basically, for every person whose score we don't know, we pretend that this score is mean score. Ivanov's IQ score is not known. Let's pretend that he has an IQ of 100. And this is a very bad approach for two reasons. One, the assumption that Ivanov's IQ is average might be completely wrong if he's a genius or vice versa. And the second reason, if you replace missing values with means, what happens with your standard deviations? What happens with your standard errors? You get a distribution where the number of scores equal to the mean is artificially inflated. As a result, your standard errors become more narrow. And all the statistical inference tests that you conduct based on these standard errors will be likely to produce false positive conclusions. Usually false positives, because you will underestimate your standard errors. So you will definitely have very biased results, and it's an approach to be avoided at all costs. Another approach, which is slightly better, is called single imputation, when you try to use non-missing values for this individual to predict this particular missing value. We often use it when we calculate total scores for questionnaires. Imagine that you have 20 questions in your questionnaire, and a person has not answered one of them. So if you calculate total score as a mean score for all the questions, it's not a problem. Just this person's mean score will be based on 19 questions instead of 20. And the amount of error that this will introduce is probably negligible. But if the number of missing answers is fairly large, and research shows that if more than 10% of answers in a scale are missing, this single imputation is going to introduce bias into your total scores and into your estimates. And the same if you're trying to use, for example, regression to predict missing values on a certain variable based on other variables. This would also essentially be single imputation, and it will not be very efficient statistically. Luckily for us, we have really good approaches, very flexible, very robust approaches that work even in case when the number of missing data is very large. Obviously, if the number of missing data is very small, for example, only 1% of your values are missing, maybe you don't really need to worry about it very much because it will not affect your results. But sometimes you might have situations when 50% of all values are missing. If you had a planned missingness design and people were randomly assigned to complete 2 questionnaires out of 3, because you wanted your total questionnaire to be shorter, then you'll have a matrix where the proportion of missing data will be very substantial. And in order to treat such a data matrix, even if it's missing completely at random, you would probably apply one of those procedures. And also those procedures can deal not only with missing completely at random, but with missing at random. So if there is some systematic reason for missingness, and if it's somehow related to other measured variables, these procedures can treat this missing data correctly and produce unbiased estimates of associations. One approach is called full information maximum likelihood. And it's an approach used by software that performs factor analysis, confirmatory factor analysis, like Amos, M+, etc. So when you model some latent variables, normally it uses this full information maximum likelihood. It tries to obtain maximum likelihood estimates for all the correlations and means in your data. And this approach is very efficient. It can deal with missing at random. However, if you want to actually recover the missing values, you can use 2 other approaches. A more simple approach is called expectation maximization algorithm, or just EM. That's why in SPSS, under missing value analysis, you get this checkbox called EM. What is expectation maximization? It takes your original data, and for your original data, it calculates means, standard deviations, and correlations between variables. And then it tries to predict missing values for each variable based on all the other variables. And it creates kind of plausible values by pointing a finger in the sky, more or less. And then for the matrix with those plausible values filled in, it recalculates means, standard deviations, and correlations, and it compares recalculated results to the estimates based on your original data. And if the discrepancy is large, it tries to adjust some estimates of missing values in order to reduce this discrepancy. And then this adjustment is made, and then the scores are recalculated again and compared again to the properties of original data. And this is performed in many steps until the algorithm converges, until the discrepancy between the parameters of restored data, means, standard deviations, and correlations, and your original data becomes very small and negligible. So in SPSS, you can basically tick save completed data, and you will get a data matrix with missing values replaced with plausible values, values that SPSS kind of expects should be there. These plausible values will be fractional, even if your original value is integer. So for example, you have answers to questions on a Likert scale from 1 to 5, and your missing values can be replaced with a value like 3.5, or sometimes it will be even 5.7. So sometimes these values can be kind of out of range. But you're not supposed to do anything about those estimates, just leave them as they are, and you can proceed to analyze your data, treating this as complete data now. However, there are two important limitations. First, this approach is based on maximum likelihood algorithm, so it's based on normal distribution assumption. Your data are supposed to be show univariate normality and also multivariate normality. So if your distributions are not so normal, these estimates of missing values will be misguided. And also, if the proportion of missing data is very large, over 10% or so, and also depending on how well this missingness can be predicted, this algorithm might not be extremely efficient. So if you have a very complicated situation when the proportion of missing data is large, or your scales are ordinal, or your data are not normally distributed, or your distributions are kind of unknown or unpredictable, what you need is another approach which is much more robust, which is called multiple imputation. Why is it called multiple imputation? Because SPSS tries to make many different guesses about the possible values that should be in place of your missing values. And in creating these guesses, it uses a very complex set of Bayesian networks. Basically, it tries to take information in your data and make different probabilistic guesses about those missing values. So as a result, it creates a certain number of data sets with different ways to replace your missing data. And research suggests that the number of these data sets should be proportional to the percentage of missing data that you have. So if this percentage is small, you can get by with 5 or 10 imputations. But if the proportion of missing data is large, you need dozens and dozens of those imputations. And SPSS creates this data matrix where the number of rows is increased by this number of imputations. And then for many different analyses, it can use this multiple imputation data. So when it calculates correlations, for example, it does not use a single imputed data set, but it takes all these imputed data sets together and it calculates correlations independently for each of these data sets. And then it pulls these estimates of correlations together, and as a result, the resulting correlation, which is based on correlations obtained for each of these datasets individually, is unbiased. It is much closer to reality, if we could know this reality. At least that's what simulation studies show. And this approach even is better for the situation of missing not at random, although it gives no guarantee, but at least it's the best approach that is available and the most robust approach that we can use. But unfortunately, these calculations based on these imputed datasets take a lot of time because they are performed many times. And also not all statistical analyses are able to make use of these imputed datasets, especially in SPSS. So if you'd like more details on missing data, there is a nice chapter in Handbook of Psychology Research Methods volume, which I strongly recommend, by Shinka and Velitzer, 2003. It's a special chapter dedicated to missing data, where you have all this discussion of 3 types of missingness in detail and the strengths and weaknesses of different approaches. If you want to actually deal with missing data, there are several very nice packages in R. There is MICE, which can, MICE is an acronym for multiple imputation, which can do really robust multiple imputation. Amelia, named after Amelia Earhart, who was missing, which has also several good options. And there is another one which is called Mismatch, also a nice one. But these are not just these 3, there are many more. In Jamovi, unfortunately, there is still no graphic interface to work with missing data, but maybe in the next versions of Jamovi it will appear, because obviously it's a very important task. So again, in most cases, you don't really need to worry about missing data when you don't have much missing data. But if your sample is very small, and if every observation is precious, or if the proportion of missing data is very large, and you want to make sure that you don't bias your results by ignoring missingness, or if the reason for missingness is systematic, it's also called non-ignorable missingness, missing at random or missing not at random, then you definitely want to use some kind of more robust approach. And in your research report, you just say, for example, expectation maximization was used to replace missing data. But if you mention something about missing data, you need also to describe how much missing data there was, and whether it was randomly or not randomly distributed. So you need to give some details on your original data and how you treated it. So this was a little introduction into missing data. At least if you face this issue, you know where to look for answers. And thank you for your attention, and see you soon in our discussion of more complex multivariate methods. Bye-bye.